Hello everyone. Today, I'm Kaustav Mukherjee, PhD scholar at Bhopal, and I'll be taking the week fifth of the tutorial. And sorry, I'm a bit weak today. I have fever. So in case I'm not audible, you can just ask me. I'll try to speak loudly. Because of the fever, I may not be able to speak very loud. Just kindly bear with me. So, I'll start sharing the screen. So, today I'll most likely talk about some of the algorithms of quantum information. So, this was the last week of quantum information in your course. And most of the gates and everything that we already discussed in tutorial were also discussed in your lectures. And today we'll be taking some of the other algorithms which were not part of the lectures. For example, the Grover search algorithm or quantum error corrections. So which these play a very crucial role in the quantum computing and quantum information theory. So having a very basic idea will be, I believe, a very useful for you in case you want to research on these. That will be just great for you. So beginning with the Grover search algorithm. So Grover search algorithm was first mainly designed or invented by Love Grover in 1996. So this algorithm was one of the most famous algorithm which showed the prowess of the quantum computing. So usually in classical computer, let's say if you have numbers from 0 to n minus 1, so let's say there are n numbers, okay. And yes, Ravi Prasant, you have a question? Okay, I think that was by mistake. Do you have a question? No. Okay, yeah, fine. So, yes, so if you have, like in classical case, if you want to search a number from this 0 to n minus 1, then what you usually do is you start from the beginning and you take on one by one. And on an average, the search time, like it usually takes n by 2 on an average. So it can be either on the first or it can either be on the last also, right? So on an average, it usually take n by 2 times to find the number. So what we call this as classical search algorithm, usually scales as proportional to n. Okay. Whereas the main finding of Love Grover was that in quantum search algorithm, it goes by root n, which we will shortly see how that happens. So this like scaling of root n drastically reduces the time for the searching. So what essentially they have used is like you use the quantum superposition principles, which are not available in the classical. And let us have a look how it is actually done. So in the lecture you have seen about the Walsh-Hadamard operation. So this operation is basically having Hadamard on all the qubits, and you must have seen in the lecture that it results in a like the whole state space. You get 2 to the power n bits. So let's say you have n qubits, so this will result into 2 to the power n numbers, right? So let us briefly see. So I'll just give a recap also. So we have seen Hadamard. So Hadamard acting on 0 state gives us root 2 0 plus 1, and Hadamard acting on 1 state gives us 1 by root 2 0 minus 1. Now if you initialize, let's say our initial state is your 0 0 0. So there are n qubits here. Sorry. So there are n qubits. Now when you act this Walsh-Hadamard operator, that is acting H cross H on the whole size state, this essentially gives us something like this: I equal to 0, n minus 1, I. And this I state is usually what your, like, let's say your 0 is basically 0 0 0 1. So there are 2 to the power n number of states that are possible. So this actually gives us the total expansion. So let's say, for example, we take 3 qubits. Okay, now for 3 qubits you have 2 to the power n, which is 2 to the power 3. You have 8 numbers. Okay, now the all possible combinations are basically, you can write your 0 as 0 0 0, 1 as 0 0 1, 2 as 0 1 1, 0 1 0, and similarly you can go to 7, which is 1 1 1. So you might have seen in your classical theory also, like when you have to find out a binary from a decimal number, all you do is you take the 7, you take 2, and you just keep on doing it. So you have 3, you get 1 1, and this is your binary, right? So for 7 you get a binary like this. So this is what you have already seen in your classical cases, and that is all we are using in the quantum. So you are just giving a notation to all the states. Okay, so for n 2 to the power n, you have so for n qubits you get 2 to the power n states. Okay, now we give them as numbers 0 1 2 n minus 1. So there are n, which is 2 to the power. Okay, so there are n numbers like 0 to 7, and in terms of qubits you write 0 0 0 0 1 0 0 0 1, something like that. Okay, now so okay, so let's say you have to find the number I naught, okay, in the string of 0 1 to n minus 1. Okay, now to find the I naught number, what you have to do is, there are certain number of steps that you have to consider. So in the first step, what we do is, so we have our wave function written in the form 1 by root n, I equal to 0, n minus 1, and we have I here, right? Now let's define another state u, which does not contain the I naught. So this is the number that you are looking for, and let's say that number is not present here. Okay, so you have root over n minus 1 because there is one number less, and you have I equal to 0, I naught equal to I naught, n minus 1, and this we say as, okay, this is just I. Now you can write the psi naught in the form cos theta by 2 u plus sine theta by 2 I naught. So this might not seem very obvious, so let me just show it to how it's possible. So here the let me write the values also. So cos theta by 2 is essentially your root n minus 1 over n, and sine theta by 2 and sine theta by 2 is your root 1 by n. Okay. So let's just briefly write it down. It's not very complex, so you can just see it directly. So I'll write the sine naught as substituting n minus 1 n, and we have the u state from the above, n minus 1 I naught equal to I naught n minus 1 I plus 1 by root over n summation, not summation. So this is just your I naught state. Right. So like this simply gets added up into the summation and you get the sine naught back. Okay. So in this form you can actually write it. Now there are certain operations that you have to consider. So there are basically two unitary operations that you will have to put it on. So let's do the first one. So the first unitary operation, u1 acting on psi naught, is essentially gives us, so u1 acting on I gives you I, and u1 acting on I if I is not equal to I naught, and minus I if I equal to I naught. So you have a conditional operator here. Okay, so this is also a unitary operator. It's like a sigma z. So when you have the same state, let's say you have operating sigma z on 0, you don't do anything, but when you act it on 1, you get a minus sign. So it's a similar operator with only having impact on the I naught. Okay, sorry about this, too much sweating for the fever. Okay, now so what this will essentially do to your state, so when you act on psi naught, so what is happening here, so you have cos theta by 2 u1 on u, and this does not contain I naught state, remember, and plus you have sine theta by 2 u1 on I naught. So this is essentially your I naught state, which means it will reverse the sign to minus. So you end up getting a psi 1 state, which is nothing but cos theta by 2 u minus sine theta by 2 I naught. So let me make a block sphere here, or just a basic circle. So let's say just get a better representation of what we are actually looking at. So this is your u and this is your I naught. Okay, now you have a circle. Okay, so a cos theta by 2 comma sine theta by 2 basically gives you something like this, where this is theta by 2. So cos theta by 2 on the x and sine theta by 2 on the y. Okay, so this was your initial psi naught. Now once you have applied the first unitary operator, what it has done is basically reverse the, I'll use another color. So it has basically reversed the y-axis. So we have minus sine theta by 2, whereas we have plus cos theta by 2 as it is. Okay, now In the second step, you use another unitary operator, u2, and that u2, what it does, so you are operating u2 on psi1, and this u2 essentially is written in the form psi naught minus I. And what it essentially does is it takes a reflection over the psi naught and shifts on the other side. So we will see how it's actually done. So this is theta, and this you will get as psi 2. So let me just show you how you get that. Okay, so you are operating u2 on your psi 1. So this is psi 0 minus I acting on psi 1. So what you get here is your psi naught stays as it is, psi 1 and minus psi 1. So this does not do. So let us just look at what we have here. Okay, the inner product of psi naught and psi 1. Okay, so we had psi naught given as cos theta by 2 u plus sine theta by 2 I naught, and psi 1 is same on u but minus sine theta by 2 on I naught. Now we know that this is an orthonormal basis, so your u I naught will be 0 because it does not contain I naught here. Okay, so only the u and I naught stays. So what we have is cos square theta by 2 minus sine square theta by 2. Okay, and you know there are numerous ways in which you can write this. So this can be your cos theta, or your 2 cos square theta by 2 minus 1, or 1 minus 2 sine square theta by 2. You can write it in any way. So here I'm going to use the second one case, and let us see how we find this theta reflection here. Okay, so writing it again, so we have psi 2 as u2 on psi 1. So we have 2 psi naught and cos square theta by 2 minus sine square theta by 2 minus psi 1, which is cos theta by 2 u minus sine theta by 2 I naught. So let me write this psi naught as well. Okay, I'll just write above. So this is your cos theta by 2 u plus sine theta by 2 I naught. Okay, if you have any questions in between, just ask me, unmute yourself and ask me that straightly. Okay, now so okay, so let me just write down the for coefficient of the u state. Okay, now the coefficient of u state essentially gives us your cos theta by 2, then there is cos square theta by 2. Let's say I take 2 cos square theta by 2 minus 1, and we have minus cos theta by 2. This is the coefficient of u state. Okay, so what we end up here is 4 cos cube theta by 2 minus 3 cos theta by 2. So we have 2 cos theta by 2 from here minus, and 1 from the others. And if you remember from the basic trigonometry functions, this is nothing but your cos 3 theta by 2. And similarly, if you do for I naught, you will find out that it has the sine 3 theta by 2 in the plus. Okay, so you're essentially, you get the psi2 state written as cos 3 theta by 2 u plus sine 3 theta by 2 on the I naught. Okay, and this is nothing but what we have estimated before. So if you add theta plus theta by 2, this gives you nothing but your cos 3 theta by 2 plus sine 3 theta by 2 on the I naught, and this is on the u. Okay, now, so let's say we name these operations. So your psi2 is obtained from u2 u1 on psi naught, and we name this as g. Okay, and when you implement this g n number of times, or let's say k number of times, then what happens? So this basically is shifting your angle each time to a k plus 1, right? So what you get here when you imply the psi k plus 1, so this is basically gk on psi naught. So what you get here is cos 2k plus 1 by 2 theta on u plus sine 2k plus 1 by 2 theta, and this is on I naught. Okay, so what you are essentially getting here is that when you get I naught, that means that this term is essentially 0 and you have a 1 for this case, right? And when does that happen? Like your psi k essentially needs to be I naught, and let's say that happens in k equal to k naught times. Okay, repetitions, we have to repeat it again and again. So this essentially happens when you have 2k plus 1 by 2 theta, or let's say I'll write this as 2k plus 1 theta by 2 is equals to your pi by 2, because you know at cos pi by 2 it's 0, right? And for similarly for 2n plus 1 pi by 2 as well. Okay, so this is the first 0. Now now you have seen in the top that we have considered sine theta by 2 as your root n. So in case of large n, so when n is very large, your sine theta basically becomes theta by 2, and this becomes theta by 2 equal to 1 by root n, right? So we are going to substitute theta by 2 here with the 1 by root n to pi by 2. So what we get as k is nothing but pi root n by, so there is a 4, let's say minus 2 by 4. This is root n. So k being proportional to root n1 was one of the major achievement of the quantum information, right? So you know how to use the quantum computing in future. So this was one of the most famous algorithm in the 1990s when quantum information were on the baby steps initially. Okay, something's wrong with it. And through this algorithm, you got to find out how you can use quantum computing for other purposes as well. Okay, and similarly, In the next case, what we are going to find, sorry, is quantum error corrections. Okay. Yeah, sure. Ask. It's a number of repetitions you need. So, yeah. So, like, sorry. Yes, so in classical sense, let's say the number you are supposed to find is at place 4. Okay. And you take 4 times to find it. It's similar to here. The k is the number of time, uh, the repetitive, how many number of repetitions you made to find the number. So this only scales in classical as n by 2. So like if there are 100 elements and your number is at the 100th place, then you actually have to go from 1 to 100 to find the number, right? So that actually gets reduced here. Yes. Okay. Okay. So in the next part was this was again one of the phenomenal contributions, and in classical information theory, you send the information from A to B. Okay. So you have seen in your lectures also that there are quantum teleportations through which you send a qubit, and in classical we send bits. So we are actually doing this all the time. Even right now when we are interacting, we are sending bits, and you are also sending bits, receiving bits all the time. So in classical case, let's say you send some information from A to B, and you have some noise that is corrupting your, let's say, data. So what I mean is that you're supposed to send a 0 to B, but while it's going to B, it is becoming 1. So that means B is not getting the essential information that you are meant to send. So there are going to be miscommunications here, right? Now, in order to, in classical theory, information theory, what one does is like they make a copy of the bit, okay? And let's say your noise only flips one of the bits, okay? So based on the strength of the noise, you can actually take a very higher number of bits, okay? So what you call it as encoding, and then at the destination you do a decoding. So what I mean by that is, so let's say you have a 001 and the noise flips one bit. Okay, so let's say the B gets a 001, or let's say a 010, something of the two. There can be 100 also. Okay, any of the three. Now, how does B decodes from this code? Okay, so you know that there is some noise which has corrupted your information. You had sent a 000, but what B is receiving is 001. So based on the majority of the number, so B will count how many zeros are there or how many ones are there, and based on that, it can see that you have actually meant to send a 0 to B. Okay. So this is what your classical information theory deals with in the error correction. But you have seen in the lectures as well that you cannot copy quantum states, right? So if you have alpha 0 plus beta 1 and you want to send it to B, let's say A has the superposition state and you have to send it to B. So you have seen in the quantum teleportation protocol in the lectures that through certain number of unitary transformation and the measurement on the qubits, you can actually send the same state to B. But what will happen if there is some noise? How will B know if the state is actually correct or not? Okay, let's say the noise do a bit flip, okay, on the 1, or let's say there is only one bit, so it might flip both the bits, uh, not both the bits, there is only one bit here, so it might actually change whole information. If there is a bit flip, it will, beta will actually get alpha 1 and beta 0, which might look similar on paper, but in practical this is an entirely different information. This makes no sense to beta. Okay, so whatever alpha tried to convey to beta was actually completely corrupted. Okay, so how do you deal with quantum error correction? So we know that we have to teleport information from one to other system, and there are environments, like there can be anything which can introduce noise. There are wires, you use optical fibers all the time. There are endless possibilities of where a noise can originate from, right? So there is like very less probability of having something which does not have any noise involved. It's like only in vacuum there is a possibility that you might not get any noise, but in realistic system, when you have to give it out to the general public, you have to use your cables and everything, there will be some noise. Okay, and in order to do the quantum error correction, what one does here, so you cannot really copy the bit and then send it. So what you do is you create a state which is alpha 00. It is similar to the classical thing, but it's not exactly creating copy of the state. Okay, so it's not like when you have alpha 0 plus beta 1 and you do it copy it 3 times. So that would have made it a lot easier. But this, as you have seen, there is a no cloning algorithm. That means you cannot clone. So this would have resulted in a different state. And what we are going to use is a simply alpha. We are going to copy the bits in that particular state. So how do we do this? So in order to do this, let's say you have 3 qubits. Okay, so there is a psi, and let's say you have 2 qubits at 0 0. Okay, now you only have to use 2 operations here. So yeah, you have already seen that this is a C0 gate. I'll give a brief recap also for you. So let's say when you have a 2 qubit C0 gate, okay. So let's say you have 2 qubits. There is a control. We call this control, and this is the one which is going to get changed, the second qubit. Okay. Now when you have C0 gate acting on, let's say 1 2, 1 is the control, 2 is on which it acts. On 0 0, it does not do anything, but when it acts on 1 0, it flips the second bit to you, so you get 1 1. Okay, so I hope this is already clear, since you have already attended the lectures in which he have also given you a very nice idea on these gates. Okay, so what this will do, the operation, so you have your psi given as alpha 0 plus beta 1, right? Now your initial state, let's say, which I call psi naught, is essentially psi tensor product with 0 and 0. Okay, so you have alpha 0 plus beta 1 tensor product with 0. So I'll write in the many body form 0 0 0 plus beta 100. Okay, so this is your sign out. Now let's operate the first C naught gate. So what you have here is C naught 1 2. So 1 is your control and 2 is acting. Okay, so what you get, so, so whenever your first bit is 1, the second bit is going to be flipped. So for alpha it does not do anything, but for beta it changes the second bit to 1. Okay, now you have a C naught 1 3 acting on state psi 1. Okay, so what will happen here is that again for alpha it doesn't do anything, but for beta, since the first qubit is 1, so the third qubit will get impacted, not the second qubit. Okay, so here the third is the target qubit. Let's say not action, these are control and target. So your beta, you get a alpha 00 plus beta 1 state. Now once you have this state, what you are essentially going to do, so your uh, quantum error correction algorithm looks like this. Okay, so you have 3 qubits and you have somewhere noise introducing a bit flip. So you know a 0 will either get to a 1 or 1 will get to a 0. Let's say this is only acting on one of the qubits. Okay, now you have on the left alpha 000 and beta 111. Okay, so now how do you get to find which bits are actually getting flipped, okay, or getting corrupted? So what you do, you take some ancillary qubits. So let's say these are in state 0 0. Okay, and you put a C naught gate so you have put two C naught gates coupling the first qubit to the first ancillary, second qubit to the first ancillary, and similarly second to the second ancillary and third to the second ancillary. Now what it actually does, let's see what happens. Okay, so let's say you have state 0 0 0. Okay, so when you have 0 0 0, that means both of these are 0. That means it won't affect it and it will remain in 0. And similarly these two are also 0, so it will also doesn't affect it and you will remain the same. Now when you have, let's say some state like for example 100, let's say that is a corrupted state, right? So you have a 100. So when you have a 100, you know for 1 the bit will get flipped. So I'll rewrite this. So after the action of 1, the bit gets flipped. After the action of 2, it doesn't get flipped because 0 does not affect anything, right? so it remains in 1. In the second case, after the action of 1, it does not affect anything, and after the action of 2 also it does not affect anything. So that means you have a 1 and a 0, which is not the initial state that you had, and this means a noise is there, or you have some corruption in your first qubit. Okay, similarly, if you take, let's say, 010, you will have a different set of such things, and from that, based on that, you can actually identify where the error has happened, and you can implement a sigma x onto that particular bit to flip from, let's say, the bit is 1, you get a 0, and you actually get the original information out, right? So what we call that as your correction. So you, after you have understood where the error has occurred, you put a correction on the bit flip. So wherever, like if it's a second qubit, what you do is you essentially put, like, the correction bit looks something like, okay, sigma x I. So this will only flip the second bit where the error has occurred. Okay, now, so till this, it is more like, in the classical sense, you have the same bit flips that is happening, but that something that is exclusive to quantum information or quantum computing only is the phase flip. So you have seen in the sigma z operation, so when you have sigma z on 0, you get 0. When you have sigma z on 1, it puts a minus sign. So this is actually a phase flip, and you don't find any classical analogous to this phase flip. So in classical information theory or classical world, this phase flip does not exist. So this is only in the quantum information. And in order to like deal with such system, what you essentially do is there are some endless number of Hadamard gates that you have to put in. So it's more like, okay, I'll draw fresh. So since you're going to refer the notes, I'll remove this. Okay, so it involves an endless number of Hadamard gates, which, so Hadamard gates can identify the bit flips, because when it has one, it produces a superposition which has a minus sign, which is different from what had in the 0. So if there are bit flips, then you can do it like through natural coupling to ancillary qubits. And when you have the phase flips, so there is a noise, let's say here, so you have to put the correction here, and you have the same ancillary qubits. So these are the quantum circuits, quantum error correcting circuits. So in let's say more mathematical terms, in order to understand this, so let's say okay, so sorry, okay, so for a 3 qubit, your bit flip error actually can be understood from operating this kind of operation. So these are you can say commuting, operators. Okay, and they have the eigenvalues corresponding to eigenvectors. Like, okay, let me write it here. So they have these set of eigenvalues. So there are two operators and we are writing in the pair. So this is, let's say, operator 1, this is operator 2, and the first counts for the operator 1, the second for operator 2. Okay, now for each pair of eigenvalue you have these eigenstates. So these are eigenvalues, these are the eigenstates. Okay, now okay, so there are different, so these are all possible set of eigenvalues, and they are actually doubly degenerate. When you try to find the eigenvalues for these operators, you are going to find the doubly degenerate eigenvalues. Okay, and the corresponding eigenstates are 0. So you can, if you want, you can do the calculations. So one, 0, 1. Okay, now now let's say you had your initial bit in the form as we have seen previously, and this essentially gets let's say flips one of the bits. Okay, so what, let's say it flips the third bit, so that means this is your third bit and the noise is acting on the third bit. Okay, so what you essentially get is alpha 0, 0, 1 plus beta 1, 1, 0. So both these third bits are getting flipped, right? Now, so you can see, so initially the eigenvalues for this state was nothing but 1, 1 for the two operators. But once you have the noise corrupting the last bit, the third bit, the eigenvalues get shifted to this one. So you get a different eigenvalue now. And based on these eigenvalues, you can actually find out where the error has occurred. And you can appropriately put the sigma x gate or your sigma z gate based on how these so what we call these as your error syndromes. So let's say when you get sick, like I am right now, there are some particular what do you say, you look for something that indicates that this is something like fever or diarrhea or something. So these are also similar in that case. So these are like error syndromes that we call. So once you have a different eigenvalue, a set of eigenvalue, you can find that okay, this is impacting on this particular part of the qubit, like this disease is impacting this particular part of the body. So similar to that. So this is what we most famously use as your quantum error corrections. Okay, now so there are other very famous algorithms. One is like the Shor algorithm. So this is one of the most famous. So like the most famous is the Shor's algorithm, and then you had the Grover's algorithm. So in the Shor's algorithm, so this was done by Peter Shor in 1994, and what it actually does is prime factorization. So I won't go into the detail because it is beyond the scope of this talk and we don't have that much time left. So it what it involves is something called a phase estimation method in your quantum computing or quantum information. And what you do is, so let's say you have a number n, and you can write in the decomposition of prime numbers. Okay, so any number you can do a factorization using the prime numbers like 2, 3, 5, 7, and everything. Now you must have seen, or sorry, so you must have seen or heard about that the prime factorization was one of the most important unsolved problems during the Second World War, or the First World War, I think, when Ramanujan was himself solving such complex problems, right? So in classical case, it actually takes exponentially. So like uh, the solving or finding out the factorization, the prime factorization for any n number is like gets exponentially difficult. Okay, but whereas from the sorry, whereas from the Peter Scholl's algorithm, what he showed, so Scholl's algorithm showed that using quantum computing and using the phases in the superposition that is only available to quantum bits and not the classical bits, this actually reduces down to the factor n. So it polynomially scales with factor n. Okay, which is like much easier compared to an exponential scaling. Okay, so when you have e to the power n, it gets very difficult, and moreover the classical computers are not that efficient as classic quantum computers. So there are informations like you might have recently heard about Google claiming that some calculations that would have taken the classical computers some 10 to the power 6 seconds, years or something, can actually be solved within few seconds in the quantum computers. So these were some of the most like what do you say, trademark of the quantum world, quantum computing and quantum information worlds. And in the recent era, so in recent times there has been a lot of development going on. So if you any of you are interested in the research on quantum computing or quantum information, so you can actually, so like IBM is building quantum computers with right now having 192 qubits, and if you see their plans by 2024 or 2025 they will have 4000 qubits. So there is a lot going on, and some new type of developments are also taking place, such as measurement based quantum computing. So till now, all the when you have these quantum gates or your unitary operators, this is something that is traditional quantum computing, which has been going on for the past few decades. And in the recent times, like what they do is you take a series of qubits. Okay, so this is something like a 2D lattice of some material, let's say. Okay, so you have these qubits. So in measurement based quantum computing you need a lot more qubits, and what they do is, like, you want to create an entanglement between this qubit and this qubit, and you basically measure the qubits around it to create this entanglement. Okay, so once you have such measurements, so they are actually using only your sigma z and sigma x measurements, and through these set of measurements you can create an entanglement. And similarly, so in measurement based quantum computing, you are not really involving any unitary operations, and you're already doing the measurement. So there's like already a collapse system. So you don't really fear of losing much information here. So these are some of the recent advancements that are going on. And okay, so maybe I don't have much to talk about. If you have any questions, or I can go through the Shor's algorithm, I can try to explain. The algorithm can be a bit messed up, or let me just check if I missed something. Okay, so sorry, because of the fever I could not prepare much of the materials. What? Yeah, I'm not well actually, yes. So yeah, that's why I was thinking of skipping the class, but then it's not actually allowed to reschedule it. So yeah, but that's why I could not prepare much of the material today. Yeah, thank you. So I think if you have any questions, you can just go on. We can chat a few minutes. Otherwise, we. Okay, okay, okay. Sure. Right. Okay. So thank you. I'll try to add some questions later on, maybe to the video and upload it. Uh, because right now I'm not in a very good position to solve any. Sarvanan, do you have any questions? Okay, okay, sure. So let's just end the class for today here, and we will meet next week. So I believe from next week onwards you have uh, perturbation theory and WKB approximation and all that. So like we are going to shift from the quantum information. So I believe this is the last class based on the quantum information, I suppose. Okay, so I don't remember a book from the top of my head, but there are like very decent quantum computing books. I can, if you can send me an email, I can actually find and send some to you. So you can write my email ID. It's Kaustav16 KAUSTAV 16 at the rate izb.ac.in. So you can send me an email and KAUSTAV 1616, yes, 16 at the rate IISERB double ISERB dot AC dot in. Yeah. So just drop me an email and I can send you the books. Okay. Okay, so thank you. Let's meet next week then.